In this section, we're going to be looking at electricity, and within this, we're going to be looking at everything as part of this, starting with symbol diagrams all the way through to the national grid and static electricity if you're studying separate science. Pay attention to the key in the right hand side. If this is in green for your paper, it means you could be assessed on this in your exam. While if it's greyed out, it means that that is not content that is on your specification and you will not be assessed on. We're going to start by looking at circuit diagram symbols, because one thing that we can anticipate in any physics exam where you have electricity been assessed is that they are going to give you circuits to kind of interpret and use as part of your questions. And it is important you're confident with those diagrams to help you just access the questions that come from this. So first of all, we've got a switch that's open and closed. A common thing they might do is ask you why this switch, for example, we will not have components on. And it's the idea that when that switch is open, there is a break in the circuit. The current cannot flow in a continuous loop all the way around. While when the switch is closed, the current is able to pass across. We have cells and we also have batteries. Now, batteries are two or more cells in series connected together. We also have a diode. Now, for a diode, we're going to draw this as a triangle with then like a line that follows this after, all enclosed within a circle. And there's resistors along the bottom here. But the common thing we'll notice in all resistors is that there are a box that has a line coming out either side to represent its connection. A variable resistor, again, we've got that rectangular box with an arrow now going through. We'll come back to our resistors, but we have LEDs and lamps. So an LED is a light emitting diode. So the symbol looks very similar to a diode, but to show that it's light emitting, we now have two arrows coming out of the component. A lamp will just be a circle with a simple cross through, while a fuse looks quite like a resistor but has the line extending all the way through. Voltmeters and ammeters, people tend to do pretty well with these ones, and that's our circle with a V and circle with an A in it. Out of all the ones you tend to get asked to draw in exams, these are the two that are the most common, and we'll touch on that a little bit later on. Our thermosistors are resistors that are sensitive to temperature, and with this we have our rectangular box with almost like a hockey stick extending through, while an LDR is a light dependent resistor. So because of the fact it's now dependent on light, we've got these arrows coming inwards representing light into our resistor. So these are the components that you need to be aware of. Anything beyond this, they will give you some detail on the symbols within the exam question itself. With our electricity topic then, we're going to start with the idea about electric current. And this is the flow of electrical charge. And in physics, this is very much down to just the flow of electrons. So we have charged particles flowing around a circuit, we will have an electric current. Those particles are electrons, and we need a complete circuit and potential difference for these to move. Our equation will be charge flow is equal to current times time. So the larger the current and the longer the time, the more charge we have flowing around this circuit. Our units, it'll be coulombs or C for our charge flow. Current is in amps or A, and time with electricity will be measured in seconds. Be prepared that there may be some unit conversions in this. So be really vigilant when you're looking at exam questions with how many marks you've been given, and always make sure you're highlighting those values and you're really clear on which values you've got, and double check each for is there a unit conversion that you need to do. So electric current then is this flow of charge of electrons around a circuit. Now, what we do have in any circuit is we'll have components which are conductors and wires that are conductors as well. And within them, we've got loads of these electrons that are free to move around. The battery, or in this case the cell, is what's causing that potential difference, which then causes these electrons to move. One important concept of electricity is the idea these electrons are not used up, but instead will flow in a continuous loop around the circuit. If we have a look at one of the first kind of calculations then, here we've got a torch that's worked for 14,400 seconds before it needs to be replaced. We're told the current in the LED was 50 milliamps and we're asked to find the charge flow. So our system for how we approach this, I'd always say kind of go through and highlight your values with a highlighter and underline or highlight what you've been asked to find. But here our unit conversion will be the 50 milliamps. So we'll convert this into amps by dividing by 1,000. Then make sure you write the equation down that you're going to use. So our charge flow is equal to current times time. And then substitute in our values. So here we've got our 0.05 from our unit conversion times by our 14,400. Now in this case our calculation is quite simple and straightforward, but here our charge flow will be equal to 720 coulombs. So current though depends on a number of factors, and what we find is that it really does depend on the resistance in the circuit and the potential difference also across components. If we've got a bigger resistance, current tends to be smaller, and our relationship is potential difference is equal to current times by resistance, or otherwise known as V equals IR. If you kind of review any of the past questions that have come around electricity, this one tends to get used the most. So this is one that I'd be really expecting to see in your science exams. Potential difference is measured in volts, current is measured in amps, and resistance is measured in ohms. And typically students do tend to be quite good at able to identify and use those different units. But do be prepared to convert them. So with that equation, in a given circuit, the larger potential difference is, the bigger the current is going to be. Now, components that we typically put into these circuits are resistors, lamps, LEDs. They resist the flow of charge, as in they make it difficult for those electrons to move through them. But for the most part, all the connecting wires that are represented by these just straight lines, generally their resistance is so small and the effect on current is so small, we just ignore their resistance in its entirety in calculations. But what we do find is that when resistance is higher, current tends to be smaller, because resistance is a measure of how difficult it is for electrons to flow. And so if we've got a really high resistance, it's going to be a lot harder for electrons to flow. The current will be smaller. So if we have a look at this question, a hob draws a current of 26 amps from a 230 volts mains electricity supply, whilst to find the resistance. Now generally in this, they don't technically have to tell you that it's 230 volt mains electricity. You are expected to know that. But for the most part in calculations, they do tend to give it. So in this one, we're going to be converting units. There are none, like amps and volts is absolutely fine. We'll write down our equation, so V equals IR. Now even though we're finding resistance, we're going to substitute. So here my voltage is 230, which is equal to our current of 26 times by resistance. So it's equation, then substitute. Only after that rearrange. The reason is it makes your marks more secure. The way in which you'll be marked by the examiner is have you given the correct equation and have you substituted into it correctly. If you give the wrong equation, and that might include rearrange the equation incorrectly, you don't get the substitution mark. So you tend to lose a couple of marks in one go. So always write down the formula and then substitute. Only after that would you rearrange. Now in this case, resistance will end up as 230 divided by 26, which will give us this, which I'm going to round in this case to 8.8 ohms. We'll pick up on the required practicals around this in a later session, but you might be asked to investigate the relationship between length of wire and resistance. Now for this, really typically what we're going to see is a circuit set up like this. We've got a power supply, we've got an ammeter within the circuit, we can connect in a device usually using crocodile clips or contact pins, and we'll have our voltmeter across. One thing not in this diagram that actually would be helpful is also have a variable resistor over here. So we've got some way of adjusting the resistance in the circuit. So we'll set up our diagram as shown, and if we're doing our length of wire, we get our length of wire and place crocodile clips 10 centimeters apart. And what we then do is we record the current and the voltage that we actually have within that circuit. And we can use that to find our resistance. What you then do is you repeat this for at least 5 different lengths, finding current and voltage for each time. And what you should be able to do is then plot a graph of resistance against length. There are certain resistors that do come up in the specification, and we need to be able to describe them and identify them from these IV characteristics. So here we've got the relationship between current and potential difference for some different components. Some are resistors, some are just components, but they all cause resistance to current. What we find is that for some of them, resistance stays the same, it's a constant, while in others, it changes, and that's where we start to see these different shaped graphs emerge. So first of all, this is an ohmic resistor. What we can see here is a directly proportional relationship. As we increase potential difference, current is increasing at the same rate. Now, the way in which we can see that this is directly proportional is that we have a constant gradient, so a straight line going through the origin. And that's a very common 2-mark question to be asked in the exam. They might ask you about what kind of relationship, they might ask you how you can tell. But when it comes to directly proportional, we've got that constant gradient going through the origin. So what this means is that if I double potential difference, I'll double my current. So one caveat to this though is this is at a constant temperature. So we do not have this wire getting hotter or colder. This is only a wire with its temperature controlled. So as current changes, the resistance is remaining constant for an ohmic conductor, provided the temperature of the wire isn't changing. Now with a filament lamp, we get an IV characteristic that looks quite different. So what we now find is that as the resistance of the filament lamp will go up, because the temperature of the filament's increasing. So the temperature in this wire is definitely not constant for a filament lamp, and what we'll find is that its resistance will increase when temperature's gone up, and it means we get this almost like curved S shape to our graph. You might be asked to sketch these in your exams. Just make sure it's relatively symmetrical around your center origin point. But with our filament lamp, we get this shape because resistance is not constant as the current is changing. So we find that actually as current increases, we're going to find the temperature of the wire increases and therefore resistance goes up too. Our last one is a diode, which looks completely different to the rest. Now with a diode, it only allows current to flow through in one direction. And the reason behind this is that in the reverse direction, the resistance is so high, the current just cannot flow. So notice with the negative potential differences, we have no current. Resistance is too high. But eventually, when we get across into the positive potential difference, the resistance will drop enough we can have current flow, and then it will increase at a relatively constant gradient. But this is not directly proportional because it's nowhere near the origin at all at that point. And remember, that's our circuit symbol for a diode. So a couple of resistors to be aware of. First of all, we've got a thermistor. Now we represent this with a rectangular box with that hockey stick kind of extending through. Now thermistor's resistance depends on temperature. And what we kind of find is that if, for example, we have temperature increase, the resistance of the thermistor decreases. So if temperature does one thing, the resistance does the opposite. So at really high temperatures, what that then will mean is the resistance is low. and so we'll have more current flowing through that component. So at low temperatures, resistance is high, while at high temperatures, the resistance is low. What this does mean is that thermistors are particularly useful in being used in devices that need a sensitivity to temperature, and so these will be used in thermostats and will have ability to turn machinery on and off depending on temperature. Another resistor is the LDR. Now, the LDR, its resistance is dependent on light, and it behaves in quite a similar way to the thermistor. So what we'll find is that if, for example, light increases, we'll find that the resistance of the LDR decreases. It does the opposite thing. So in dark, or when light levels are really low, what we'll find is that at low light, we're going to find resistance is really high, and therefore current will be low. It can't travel through. So it's that almost like sequence of events. There we've got high or low light intensity, I should say, therefore high resistance, and then for a low current. And it is a really common thing that might be worth 2 or 3 marks in the exams to talk about the effect of a change in conditions on an LDR and on a thermistor. End it with your current. So if we've got the resistance or light intensity going down, resistance goes up, therefore current goes down. So it's that up, down, up. And they're doing opposites of each other. In bright light though, when bright or light intensity is really high, what will then happen is the resistance is low and therefore current is high. What we can find is that LDRs are particularly useful in circuits where we need some sensitivity to light. What we will find is that overall, if we are affecting the resistance and the current, generally what we'll find is that in a series circuit, for example, we'll find that potential difference will remain the same. But you do have to be quite careful when you're looking at parallel circuits about how that might be affected. But in a simple series circuit, what we'll find is that if resistance has gone up, current's gone down, we'll find that potential difference will remain the same within there. But we'll touch on how it might be affected when we look at series circuits, or parallel circuits I should say, in a little moment. So, and that little moment's now, in that we need to be aware that similarities and differences between series and parallel. As an easy one marker, they might just ask you what kind of circuit you've got or how components have been connected. And what we've got here is our series circuit. These components are in series because current has to flow from one through to the next. While this circuit is in parallel, we have these branches coming off. We've got different routes that current can take. So these are the 2 ways that we've got of joining those components together. We can have components in series, we can have components in different branches in parallel. Some circuits will even have combinations of both. You might have a branch with a couple of components in series and then another branch in parallel across it. A really common 3-mark question is you might be given a circuit and asked to draw an ammeter and voltmeter into it. What the examiner is going to be assessing for those 3 marks is, do you know your circuit symbols for ammeters and voltmeters? And they'll give you a mark for that if you know both. Do you know how to connect an ammeter? And do you know how to connect a voltmeter? Now, our voltmeter will go in parallel across the component you want to measure the potential difference of, while ammeters will be connected in series. So it's always, when you're looking at current, put it in the same loop. When it's potential difference, you need to put that in parallel across. So in series circuits and in parallel circuits, what we do tend to find is that what goes on with current and potential difference and resistance is a little bit different. And you need to be aware of what's going on with each and able to use and apply this in exams. So first of all, in a series circuit, it doesn't really matter where we kind of test the current. It will be the same all the way around this branch. So all across this loop, the current will be the same everywhere. While the potential difference is shared or split across the components. So let's say this battery or cell I should say, has got potential difference of 3 volts. If these are the same resistance, this bulb will take 1.5 split and this will take a 1.5 split. So the potential difference is either shared or split across these components. And the resistance, you add them up. So they each have their own resistances, the current has to travel through each of them, and so the total resistance of the circuit is the total resistance of all the different components added together. And remember, a wire has got such low resistance, we basically can ignore that. That's negligible within that calculation. But all this means is our resistance total is equal to the resistance of our first component plus the resistance of our next. So there's only 2 in here because there's only 2 components. If there were more, you'd have to add those in too. Now in a parallel circuit, what we now find is the potential difference is the same across each branch. So if, for example, this cell still had a potential difference of 3 volts, this branch would have 3 volts and this branch would have 3 volts. What this would mean is these bulbs would be brighter. They've got a higher potential difference across them. Now the total current is actually, we have to add all our branches together. So the current through this branch and this branch will combine to give the total current over here. So what we now find is potential difference is the same across each branch, but now the current is split. It goes across each of those branches, totaling up over here. Now, every time we add another branch and electrons now have more options about the route they take, this lowers the resistance. So actually, if we were looking at the resistance of this circuit, it will be lower than the resistance of each of the components. If we have a look then, we've got 2 circuits and which one's got the higher resistance and why? Now, both of these circuits are in series, and so what we're going to find is that B will have the higher resistance. This is because of the fact that we have got the electrons having to move through both of these components, so they get added together. So the total resistance is the combined of both of these. Now I've still got 2 components, but they've now been connected in a different way. Now which has got the higher resistance now and why? It will be A. So what we find is that when we add more and more branches to a parallel circuit and there are more and more routes for the electrons to take, resistance drops. Actually, B, because it's got twice the routes, has got half the resistance of A. So A has got a higher resistance here. So every time we add an extra branch to a parallel circuit, there are more pathways for that current to flow, the resistance decreases. So because there are twice as many paths that this electron could now take, the resistance is actually halved by adding in an extra resistor. Now to summarise this, the general rules of this is that in a series circuit, current is the same, while in a parallel, it's either split or shared. With potential difference, in series, this is now shared, while in parallel, we find that potential difference across each branch is the same. With resistance, in series, it's the sum of everything, while in parallel, the total resistance is actually less than the smallest resistant component that we've got, or lowest resistance for a branch that we've got in that circuit. So the rules around this are slightly different. Now, it depends on your kind of confidence going into the exam with what happens with series and parallel circuits. But there is nothing stopping you in the exam before you actually start your paper on your equation sheet, just making a quick note. So we have this idea that we can have direct and alternating current. With direct current, it's kind of hard to write as a definition, but direct current is a current that moves in the same direction, and this comes from cells and from batteries. Alternating current is a current that is changing direction. And with this, it's where we have our current in our national grid. You do need to know a couple of fact recalls with the national grid. So first of all, mains electricity is an alternating supply. It has a frequency of 50 Hertz and the potential difference is 230 volts. As I said earlier, this tends to get assessed as 1-mark questions rather than getting you to calculate, for example, doing an equation and missing off the potential difference of mains electricity. They do tend to give that when you're looking at calculations. But still, it might be like a grade 8-9 question, so it is something to be aware of. Now, how does a plug work is then onto the next kind of section. One thing that we do need to know is the colour of each of the wires and what they do. So most appliances have what we call a 3-core cable, where we have these 3 different coloured wires within the plug. And for colour coding, so we know which wire is which, we have a different colour on each so that we can identify these easily. Now the live wire is in brown and it should always be the one that's kind of tucked in next to the fuse. Its job is to carry the alternating potential difference from the supply. And so the potential difference in this wire is huge. It's 230 volts. Now the neutral wire is blue and its job is to complete the circuit. It has pretty much potential difference of 0 or very, very close to 0. The earth wire is a safety wire that is this green and yellow candy stripe colour. And its job is to stop appliances becoming live if maybe the live wire becomes like a loose connection. Its potential difference should be 0 volts. There actually should be no current running through that wire at any time. The only time it does run through it is if there has been a fault in the circuit. So live wires, it's that idea that we always need to be wary of them. Even if the switch is open, they still have the potential to possibly cause harm. Now with this, is the idea that if we did inadvertently complete the circuit accidentally one way or another, you'd have that huge potential difference of 230 volts. And the risk to us there is electrocution. Now the live wire and earth wire should never be connected. And the idea here is that if we do have these connected, we're now going to have, occurs in a fault, what will happen is the earth wire will take the current and it will go to the ground. And the hope is it flows through that wire because it's a lower resistance than it flows through you. You're higher resistance, and so if there has become a fault with that appliance, the current should flow through the earth wire rather than through you. So it offers some protection to us. But it still shouldn't be carrying that potential difference. There's a fault that's occurred. What that can mean is we can get overheating, we can still have shocks, and there can be fires also. Now power, there's a number of equations within your exam to be aware of. Power is equal to potential difference times current, and power is measured in watts. Current in amps and potential difference is in V. But there are a few equations, as I said. Power is also equal to current squared times by resistance. So resistance is measured in ohms, and you might be asked to use both of those equations. And they commonly link it to domestic appliances, which are objects in our home that are designed to bring about useful energy transfers. And what you tend to find is that the more energy an appliance transfers, the higher that power the appliance is and the longer it's been turned on for. So that gives us a really good idea of this. Now, typical transfers that take place can include quite a wide range of transfers, but they'll all take in electrical current and transfer it into something else. So light bulbs will transfer this into light. We'll have a blender transferring it into kinetic energy to mix food. A kettle might transfer electrical energy to transfer it into thermal to actually heat that water up and boil it. And a fan can transfer it electrically and actually then but a fan can transfer electrical and transfers into kinetic energy to have this movement, and actually will have that air moving to create this airflow. A drill can transfer electrical energy into, again, this kinetic energy. and an oven will transfer it into thermal energy to cook. Now those are the useful transfers. Linking into energy and efficiency, we are going to have heat dissipated, and that tends to be where the energy will be lost here. So energy transferred is equal to how much power of the appliance multiplied by the time at which that appliance is on for. Energy is going to be measured in joules, while power is back to watts, and time will be measured in seconds. Be wary, there is that idea, just be always on the lookout for those unit conversions. So if we have a look, a toaster is on for 1 minute and has a power rating of 800 watts, and we're asked to find the energy transferred. So we'll go through, highlight our values, and in this case, our unit conversion is 1 minute, which will be 60 seconds. So slightly different unit conversion there. We'll write down our equation, substitute in our values, no rearranging needed, and find our final answer of 48,000 joules in this example. Now, electrical work is when we transfer energy from one store to another, and this happens when we have charge flowing in a circuit. So we know that energy transferred equals power times time. So that's one equation that we could use for this, but also we could use energy transferred is equal to charge flow times by potential difference. So there's quite a lot of electricity equations that could come up. Again, we've got our energy transferred in joules, and this is now down to our charge flow in coulombs times by potential difference in volts. If we look at this example, same kind of process, we'll go through, highlight our values, look for our unit conversions. So in this case, it's here. We'll substitute in to our equation, and notice we're looking for charge flow, but we won't rearrange just yet. So we'll put in our values, then work through and rearrange, and give our final answer with our units. So in this case, 110 coulombs. So there's quite a few that's come up in the last few minutes. We've got energy transferred, and we've got power times time, and charge flow times potential difference. If you are doing higher, you stand the chance of possibly being asked to do a multi-step calculation. This is where you use two equations minimum to find a value. So with these equations, it does mean that maybe they want you to find energy or time, but they don't quite give you enough information for power, and you could actually then go and find the power using these two equations. Or in this equation below, charge flow, well actually we could find that using current times time. And potential difference, for example, we've got V equals IR. So with these equations in particular, be on the lookout that you might need to use another equation beforehand. But the giveaway here is it'll be worth 5 or 6 marks. And you'll kind of notice in your question, they've given me a lot of numbers. This is where highlighting, knowing your units becomes really important. So that would be a more complex equation. You'd only find it on higher, and it would be worth 5 to 6 marks. And it generally it's someone who'd be getting full marks on that would be looking at getting an 8 or grade 9. So the relationship between power ratings and the change in stored energy is that if a device has got a higher power rating, it is going to transfer more energy at a faster rate. As the final section for the content that's on both combined and on higher, or combined and on separates I should say, we've got this idea about the national grid. Now electrical power is transferred from power stations to consumers using this national grid, and you might be asked what it is. Now the national grid is a system of cables and transformers that link power stations up to households. There are two common questions that get linked to this, and they come up a lot. One is what a step-up transformer is and why we use them. And it's a common 3-mark question. Now, a step-up transformer increases for 1 mark the potential difference. So for that first mark, potential difference is higher. That then, for the second mark, reduces current. And what this will do is it reduces the energy transfer to the surroundings, and so actually makes that transfer of electricity much more efficient. So for those 3 marks, it's the idea that step up, make the potential really big, or the potential difference really big. That the current is reduced for that 2nd mark, and this reduces energy transfer to the surroundings, making this more efficient for the 3rd mark. Another alternative 2 marker is you might be asked why we have step-down transformers in the national grid. Now these are usually quite close to our home. So for 1 mark, the step-down transformer decreases the potential difference. And for that 2nd mark, it's the idea that this is done for safety. So 230 volts goes into our homes, but it's a much higher voltage in the cables as part of the national grid coming to our homes. But we lower that down for safety. Usually it's such a short distance at that point from the step-down transformer to your home that the electricity that's transferring the heat, because of the higher current at this point, isn't so much of a concern. Moving on to the separate signs only content for electricity, we've got this idea about static and charging objects. Now with this, we are going to have insulating materials, and the key idea here is we have insulators that rub up against each other, and as this happens we have electrons transferred from one object to another. Now the one that gains electrons is going to become negatively charged, while the one that becomes positive or loses those electrons is going to become positively charged, and they can interact with each other. So in this case, this plastic rod has become negative, while the cloth has overall gained a positive charge because it's lost some negativity there. These objects, when they're electrostatically charged, can interact with each other when they're brought close and get within each other's fields. Oppositely charged objects are going to attract each other, while objects that have the same charge will repel each other. There's a few examples that have come up in past exam questions. So when 2 objects that are charged are brought close together, they can exert a force on each other. If they have different charges, they will attract. If they have opposite charges, or the same charges I should say, they're going to repel each other. And these are both examples of non-contact forces. There are a range of examples that have come up that you might be asked to explain. We'll have a look at the attraction of a charged balloon in a wall in a moment. We've also got these charged cone picking up paper. We've got lightning as well, and we also have static shocks. So with this balloon, it's sticking to a wall, and what's happened if we look at this side of the balloon is it's gained a negative charge. So it's probably been rubbed, there's been friction, and it's gained electrons. Now what it does is it attracts the positive to it in the wall, and at the same time repels the negative electrons. And so what we get is this layer of positivity on the wall surface, causing them to attract, sticking that balloon to the wall. So that balloon's got that negative charge, and it attracts the positive charge on the wall to the surface while also repelling that negative charge. And as a result, we're going to find the wall and the balloon stick together. Here we've got a charge cone picking up pieces of paper for a very similar reason. So what we'll find is that it pulls the opposite charge towards the surface of the paper, repelling the light charge away, causing this overall attraction. So we induce this opposite charge in the paper, and they'll now attract and stick together. Now we sometimes get a static shock, and this is down to the fact that as we walk, we might also have a transfer of electrons due to the fact that we're wearing like socks, possibly rubbing on carpet, where we've had some friction and a transfer of electrons. When we then touch another object, what we might find, especially if it's a conductor, is there's now a potential difference between us and the object. And what will happen is the electrons will move quite quickly from that person to the conductor and will earth the charge, but we feel that discharge. And that's what the static shock is going to be. And it's an example of sparking. Sparking can tend to be quite dangerous, especially if this were to happen where we might have fuels or gases that are really flammable around, especially if there's quite a high supply of oxygen as well. Because what the concern is that we have a spark that could actually cause the fuels to ignite, causing a huge explosion. So there is a concern around this in petrol stations where we've got huge tankers of fuel stored. And again, it's one of those reasons why smoking and mobile phones are not permitted when people are refueling at the pumps. Sparking is also quite dangerous for us, not just for explosions, but down to the fact that if we touch something that's got a huge electrical charge to it, that flow of current or charge through our body is what's going to cause an electric shock. And this can cause burns, but also has the potential to cause the heart to stop beating. One way we can remove that level of dangerous level of charge is to have earthing. So this will get the charge to move through the earth, in this case the earth wire, be low resistance, and that will remove that excess of charge. Charged objects can have an electric field, and this is an area around the object where they could influence other charged objects. So this is the area where we might see attraction or repulsion happen. So anything that's got a charge to it will have an electric field around itself. And the closer we are to this, the stronger that charge is going to be. While if you get further away, the field is going to get weaker. So as soon as we place another object within that field and it intersects those field lines, it could experience a force. So as we get closer, that field is stronger, we'll have a larger force, while if you get further away, that force is going to get weaker. Here we've got an electric field pattern for an isolated sphere. So notice we've got a positive charge, we have our field pattern extending out and pointing away from that positive charge. You need to be prepared to draw this in your exam, and they might ask you to draw this for negatively charged spheres, in which case you draw exactly the same thing, but you'd have a negative in here and your arrows would now be pointing inwards. So any negative charge, your arrows would just point in the opposite direction. Sparking, and lightning is an example of this, can happen when we've got a huge buildup of charge. Now what we can find is that field becomes strong enough, what can actually do is force charge through an insulator, causing a spark to occur. Now this can also happen if a charged person touches a conductor, and that's when back to what we talked about earlier, that's when we experience a static shock.